All right, let's take a look at 10.2 properties of liquids. So intermolecular forces are going to explain pretty much everything, boiling point being the most important. Boiling point is a direct measure, well, as direct a measure, I suppose, as we can have of intermolecular force strength. Again, knowing the boiling points gives us some idea of the intermolecular forces, but knowing the intermolecular forces gives us some idea of the boiling points. So they're kind of linked that kind of way. Quickly, the boiling point is the point where the vapor pressure equals atmospheric pressure. And we did talk about this in the gases chapter, but if I have a beaker with some amount of water in it, or some amount of something in it, the pressure of the vapor is essentially a liquid trying to become a vapor is pushing up. And then you have the pressure of the atmosphere pushing down. So as soon as the pressure of the vapor becomes greater because of increased energy, typically heat, what you see is it overcomes the top. Essentially, it overcomes the pressure of the atmosphere, and it boils. So that's what we're looking at. So factors affecting boiling point, molecular weight, and intermolecular forces. Basically, I'm just going to do the summary again. And this is really the most important thing to keep in mind when you're looking at intermolecular forces in terms of boiling points, surface tension, those types of things. So London dispersion forces, nonpolar. An increase in molar mass is equivalent to an increase in dispersion forces. Or I guess I should just say London dispersion forces. So for dipole, an increase in polarity as it's measured by dipole moment, which is mu, okay, is equal to an increase in dipole. And then finally, hydrogen bonding. And again, you need something polar in order to have hydrogen bonding. It increases the number of hydrogen bonding sites. Equals an increase in hydrogen bonding and stronger intermolecular forces. So yeah, that's it. Those are the kind of the keys in determining the strengths of these different intermolecular forces. And we can use these to determine different properties. The stronger they are, the better off we are. So these are some examples that we're going to try to do. List the different compounds that you have. Again, I'm going to change this. So I think I'm going to use butane, CH3, CH2, CH2, CH3. I'm going to use CH3, CH2, CH2, F. Okay. And so that's in place of that one. I'm going to use these two alcohols. 1, 2, 3, OH. So this is CH3, CH2, CH2, OH. And then finally, OH is on both ends. If you actually do the calculations for this, what you're going to find out is the molar masses are about the same. That should tell you something about the, well, that should tell you something. Okay, so list these in order of increasing boiling point. Okay, we'll use the examples that I wrote instead. Which substance, acetic acid or 1-propanol, is expected to have a higher boiling point and why? So you should draw those out. I can tell you acetic acid is kind of the standard. And 1 propanol, we just drew it actually above, but which of those expected to have a higher boiling point and why? Okay, good. So I absolutely love this plot, and there's a reason for it. It kind of sums up everything all together. So explain this plot to me. There are 3 things that you should see here. Use intermolecular forces to kind of explain your answer, but let's explain this plot. Yeah, let's explain this plot. Okay, so that was boiling point. Boiling point is the biggest one. That's why we spend the most time on it. All of that previous stuff was above boiling point. So let's talk about other properties that have to do with intermolecular forces. First of all, cohesive versus adhesive forces. So cohesive forces are attractive forces between the same molecules, same molecule type. So for example, if I have a container of water, a water in a cylinder is typically what we look at for this question, but water's interaction with itself. So how the cohesive forces are what are holding water together. Video just disappeared. There we go. So yeah, so it's basically just water holding on to water. Any cohesive force is something interacting with itself. Adhesive forces are again the attractive forces between different molecules or substances. Okay, so in the case that we're about to talk about, the example is going to be water and glass, or silicon oxide, as it were, but the interaction between water and something else. Okay, so in this case, we have water in a container, and it's the interaction with water with itself. So let's take a look at a meniscus. Hopefully, we know that a meniscus is the curved surface of liquid in a cylinder. Okay, so the curved surface of liquid in a cylinder. And we should know that, let's say that we put water into a cylinder. So this is kind of where the meniscus happens. We typically see it look like this. Okay. But if we actually do mercury, if you take a look at mercury and you put that into a cylinder, what you actually notice is mercury is going to have that type of surface. So yeah, so mercury has a convex curve. So it actually is pointing upward. Why is this? Well, this all has to do with the cohesive and adhesive forces. So if we imagine this is the wall of our, of our graduated cylinder. Okay, so on the left-hand side, I have glass. On the right-hand side, I have water. Well, what exactly is going on here? Why is this curved? And we can explain that with intermolecular forces. So glass is made up of silicon oxide. So you essentially have this network of rotating silicons and oxides. And onward forever, oxide, silicon, oxide. The surface of these things, these oxygens are negatively charged. So we do have kind of that surface of these really nice negative charges. But silicon, on the other hand, is more dispersed because it is more polarizable. And because it's more polarizable, we can actually consider the surface more negative in character, at least in certain regions. This has got really kind of a negative surface near those oxygens because they're so small and compact and very highly electronegative. Well, if we bring a couple of water molecules nearby, we see something interesting. So we know that hydrogen is the positive part of the water molecule. So hydrogen kind of lines up next to that oxygen. And then that first hydrogen attaches kind of there, creating a good kind of connection with that oxygen. And then again, hydrogen bonding continues to happen. And you have water molecules that kind of pile up, taking advantage of that hydrogen bonding network. And I'll use a different color, I guess, for this. So these little lines, these little red lines are where hydrogen bonding is occurring. And that continues, kind of continues all the way up. It continues all the way up this surface. So you just keep building, oh, another hydrogen here, oxygen, hydrogen, hydrogen up here, oxygen, hydrogen, oxygen here. Exaggerating a little bit here, but you get the idea. And it just continues on. But what you notice is these water molecules climb the surface, and there's our curve. So this curve happens because the cohesive forces, right? So this right here, or I guess I should say this right here, is going to be a cohesive force, or sorry, adhesive forces. Those adhesive forces are very strong. So when we look at water, we find out that those adhesive forces are actually greater than the cohesive forces. We have better bonds between the glass because it's so negative and it's ionic almost. And so the adhesive forces are winning and we see it climb the glass. But in the case of mercury, mercury likes to stay with itself. So the adhesive forces are actually weaker than the cohesive forces. Mercury doesn't want to interact with the glass. In fact, it's going to kind of clump up and push away from the glass, and that's typically what we see. So instead of seeing these mercury molecules are essentially just going to stay with each other, and they're going to avoid trying to interact with the charged wall. So that's why mercury looks that way, is because the cohesive versus adhesive forces are so different. All right, so let's take a look at this idea of capillary action. So again, the idea of a meniscus is caused by the strength of those intermolecular forces. Capillary action is the rise of water, or really a liquid, in a capillary. And the equation is right here. So the height, the height is equal to 2 times T, which is surface tension, times cosine of the angle of which you're contact with the liquid. So typically you're putting it in straight down, so it's 90 degrees. R is the radius of the tube. D is the density of the substance you're talking about, and G is the acceleration of gravity. So ultimately we can kind of, I'm going to rewrite this quickly. Height is equal to 2T cosine theta. If we're just looking at the differences of this, we know that gravity is not going to change, so we can kind of eliminate that. And if we assume the same substance we're looking at, density kind of goes away. The angle, if we're assuming we're putting it straight down, we can ignore the angle of attack. The surface tension, if it's the same substance, should be the same as well, and essentially 2. So all of those are going to combine to give you a constant. So really what it is height is dependent on radius ultimately, because none of these other things are really important. They just become one constant. So ultimately height is inversely proportional to radius. So as height increases, or I'm sorry, as radius increases, we expect to see a decrease in height or vice versa, right? So if we look at water in these cases, we actually see that water is going to, let's say, be here for the first one. It's going to be a little bit higher for the next one and even higher for the last. Again, smaller radius, higher height. What about mercury? Actually, mercury is interesting because it's quite because it's opposite, because those adhesive forces are stronger than the cohesive forces. Sorry, yeah, the adhesive forces are stronger than the cohesive forces. What you actually see for mercury is the opposite. So you see this instead. So this first one looks like this. This next one looks like this. So it's actually going in the opposite direction. So the height based on where you start, but cohesive versus adhesive forces is important. Good. Okay. Next random question. Why does a paper towel wick up water? And this right here is cellulose, which paper towel is made of. So why does this do a great job of wicking up water? Great, let's look at some of these other concepts quickly. It's pretty straightforward for most of these, but pretty neat actually ultimately. So viscosity. Viscosity is related to the ease by which these things slide past one another. So if you have a molecule and they have interactions, it's how easily they can transit. One of them can transit past the other. And ultimately what we notice is the increase in intermolecular forces generally leads to an increase in viscosity. But an increase in temperature equals a decrease in viscosity. As you heat something up, it runs quicker and faster, right? So here's a handful of viscosity measurements on a bunch of different substances. Honey has a really high, motor oil have really high viscosities, mostly due to the fact that they're very good at they have lots of London dispersion forces because they're really large. In the case of honey, honey also has a lot of hydrogen bonding, and because it's a bunch of sugars, and so it has a really high viscosity. Motor oil is just purely London dispersion forces, and that's why it is where it is. All right, next up, let's take a look at surface tension. Before we look at surface tension, let's take a look at adding vectors. I think we've covered this before, but we'll do it again because it's worth it. So adding vectors. If I have, first of all, a vector is something with direction and magnitude. So if I have my little arrow down and then I add to it an arrow going to the right, the resulting vector is going to be what? Well, we do this thing called tail to tip. So actually I can just probably copy this. So to make sure they're exactly the same. So in order to figure out exactly how these are going to line up, I'm going to put the tail of my addition on the tip of that. And then I'm simply going to add them together by combining those vectors. So that is the combined vector of this. So that right there is the combination of the two vectors. So it should look like that. So it's a combination of the two. You start from where you start. And that is the resulting vector, okay? The combination of those two. Good. So what does this have to do with surface tension? So we've got two different types. So if this is a bunch of molecules, I recognize this is a little bit extreme, but that's fine. So if we look at this, we have two types of molecules. I have ones on the surface, and I have ones that are below the surface. So we're going to look at these both separately. So if we take a look at the one on the surface first, this one on the surface is being pulled. We have interactions with the guy on the right, with the one on the left, and the one below, and that is my surface molecule, okay? So if we look at that, if we look at the vectors of this, the one on the surface is being pulled to the right, is being pulled down and is being pulled left. So the end result is when I add those vectors up, I have a net downward pull, net downward force on that surface molecule, okay? So all of these on the surface are being pulled down. So every single one of these is being essentially pulled in being pulled down by the molecules below it. The net result of those forces, that's what it is. If we take a look at one of these on the, I should quickly mention, it is being pulled forward and backwards because we have molecules in front and behind, but ultimately those are not, I mean, it's happening for everyone. So we can kind of ignore that one. The one that is below the surface at the center, or somewhere below the surface, you have it being pulled right, you have it being pulled left, you have it being pulled up, you have it being pulled down, forward and backward. So if I add these vectors together, the net result is 0. So there is no net force on this. So what this means is surface tension, the ones on the surface are being pulled down ultimately, and everything else is just good. There's no net force on it. So it's not being pulled in any specific direction. That's why when we drop some type of water on the table, it forms a sphere. And in fact, why it would form a sphere if it were in 0 gravity. Again, the idea is those surface ones are getting a net force pulled inward, which creates this round shape. Everything is pulling in from the center. I should mention that King Rupert's drop, take a look at that. It's when you take some molten glass and you drop it in water. And what happens is as soon as you drop that glass in water, so it would look something like this when because it cooled really quickly. If you drop King Rupert's drop in water, these outer ones have cooled really quickly. And so they've created this nice, strong network on the outside because they've all cooled together at a very fast pace. But the ones on the inside are kind of all out of sorts. They're all mixed up. They haven't had time to adjust. They've cooled more slowly and they haven't crystallized properly. So if you clip that, the entire thing explodes because the inside region of King Rupert's drop is really disordered. And because it's disordered and not structured well, it hasn't had time to set, it explodes. So it's actually pretty spectacular. There's some good videos out there for it. So check that out. All right, we're going to move into phase transitions next.